Good. So this is a joint work with Beniamino Accattoli and Gabriele Vanoni. So let's start by talking about reasonable cost models and reasonable computational models. So a computational model is, if you like, an automaton-based way of computing functions. So from any input x, you represent the input x as a state of your automaton, and by little elementary steps, you go towards a final state from which you can extract the result, namely the value of your function on x. And you would like this automaton to be such that each transition is elementary enough. It's not only effective, but it can be implemented, let's say, in constant time or in very low, with very low time complexity. And if you do that, you can arguably say that your computational model induces a notion of time and also a notion of space. So the time is modeled as the number of transitions, while the space is modeled as the maximum size of the configurations you encounter along your computation. So there are many computational models, as we all know. For example, Turing machines are arguably the standard reference computational model, and in this case, the fact that each step is elementary is, of course, very easy to realize. But we also have different computational models, like, for example, random access machines, which are the reference models, the reference model for, say, the concrete complexity of algorithms. Nobody studied the complexity of algorithms directly at the level of Turing machines. On the other hand, Turing machines and random access machines are, in a sense, equivalent, as we all know, and that's what we mean by reasonable. Turing machines and random access machines simulate each other with a polynomial overhead in time and with a linear overhead in space. This way we can, for example, dub a problem to be in polynomial time, in the class of polynomial time computable languages, either by looking at Turing machines or by looking at random access machines without any ambiguity. And the same thing can be said about logarithmic space computable problems. But the question is, what happens with functional programs? Can we give functional programs the same status as we usually give to Turing machines or random access machines? Actually, this is a problem we have been working on. A little community of researchers have been working on for years now, and this paper and this talk will be about, in particular, the aspects related to space. But let's take a look at what happens in time first. And let's do that by looking at the Krivine abstract machine. Thomas has talked about a much more sophisticated machine. The Krivine abstract machine, on the other hand, it's arguably the simplest machine for lambda-calculus evaluation. It implements a weak call-by-name evaluation. It's based on environments, closures, and stacks. And compared to the machines we saw in the previous talk by Thomas, well, it is extremely simple in the sense that it has just 3 rules. Configurations are triples of a term, an environment, and a stack. And you just need 1 rule for each operator in the lambda calculus, 1 for applications, 1 for abstraction, and 1 for variables. There are a couple of things I want to observe about this machine. The first one is that in the first rule, you see environments duplicated, copied. And typically, you actually implement this copying by sharing, as we already seen. This, of course, is done for the sake of being efficient in terms of time. On the other hand, you have a crucial invariant that is the following one. Every reachable configuration is such that all terms appearing in the configurations are subterms of the initial term, which is very good. This means that you don't create new terms. You just navigate inside the initial term, as far as the first component is concerned, of course. And the theorem, which has already been mentioned, is that the number of reduction steps in the Krivine abstract machine is a reasonable time cost model. From that, as Beniamino said in the first talk, you can even derive an invariance result telling you that the number of beta steps is an invariant cost model, is a reasonable time cost model. Very good. So, by the way, let me stress that by reasonable, what we mean is that there are polynomial overheads between the lambda calculus on the one end via the Krivine abstract machine and Turing machines and random access machines on the other side. Okay, good. So let's take a look at types. We would like to reflect the time behavior of terms compositionally in a type system, so as to be able to reason about it not by just the operational semantics by the machine, but by way of types, which are inherently compositional. So suppose you have a computation starting from the initial term for the initial configuration from T, and it goes through some intermediate configurations. Since U is a subterm of T, you know that in any type derivation for T in simple types, for example, well, U is there, right? Because it's a subterm of the initial term. The point is that this correspondence, the correspondence between configurations and subderivations is not injective at all, because the same subterm can be encountered in many different places along the computation. So the size of derivation arguably tells you nothing about the complexity of reduction. The situation changes dramatically if you switch to multitypes, which, as Beniamino said, they are just our name for the so-called non-idempotent intersection types. In non-idempotent intersection types, actually, you are not so far conceptually from simple types. What you have is that on the left-hand side of the arrow, you have not just one type, but a multi-set of types. You type variables in typing judgments with multisets, and you treat these environments much in the same style as you treat environment in linear type systems. So these multisets just are added up, for example, when you type applications. So if you do that, if you use multi-types rather than simple types, well, you still have, of course, this picture. You still have this correspondence between configurations and sub-type derivations. The point is that this is now an injection. So every configuration, better, two distinct configurations you encounter, well, they correspond to distinct subderivations. This means that the size of type derivation tells you a lot about the time complexity of a term. And indeed, you can even go beyond that and say that you label your typing judgments with actually a weight, which tells you better how many rule instances you find in your type derivation, roughly speaking. Weights are just summed up along the type derivation. I'm sorry. And you can prove, as De Carvalho did in 2006, that multitypes are a sound and complete methodology for deriving the time behavior of terms in the Krivine abstract machine. So every closed term reduces in W steps, if and only if it can be typed with weight W on the type star, because star is the type of the results in multitypes. Very good. So now, let's take a look at space, because we would like to do more or less the same thing, but with space. The point is that if you just take a look at one computation in the Krivine abstract machine, and you focus on your beloved intermediate configuration UE pi, you would like to say how big it is. The point is that, well, you use sharing, right? You want to use sharing because this way you are efficient as far as time is concerned. The point is that if you use sharing, well, space becomes essentially unaccountable. When are you doing garbage collection? Are you using reference counting? What's the cost of it? What's the space cost of it? So sharing makes space a little bit more difficult to be dealt with, and so it must be done with great care. On the other hand, closures tend to become unnecessarily too deep. You can easily form closures made of chains of variables, and of course this is not good from the point of view of space. But fundamentally, say the main problem I would say is that, well, where is the input? Well, when you want to evaluate the space consumptions of algorithms, typically the input is outside of the picture. You don't want to count the size of the input in your space consumption because you want to deal with things like sublinear space algorithms. Where is the input here? Well, intuitively it's t, but t, well, it's a bit everywhere in U, E, pi. Okay, so all these problems must be dealt with. And this is what we did this year, actually, by introducing what we call the space Krivine abstract machine, which is a variation on the Krivine abstract machine in which space is dealt with great care. So we have 5 rules instead of 3. We have 2 rules for applications, and the first one implements a standard technique to deal with this chain of assignments, of this chain of variables, which is called unchaining. Indeed, when the argument is a variable, you can just shortcut everything, and this is quite convenient. The second rule tells you that copying is indeed performed, but only when necessary. This operator bar T stands for sort of a projection operator on environments. And on top of that, sharing is by design limited to terms. We don't share at all environment. We don't share at all closures. We only share the initial term. This is implicitly a way to account for the size of the input. Only the terms are shared. Finally, the third rule tells you that we do garbage collection, but in a very simple, trivial way, namely in an eager form, namely whenever we realize that the variable simply does not occur free in the body, well, we can, again, shortcut the whole thing and do some garbage collection. And at LEAKS this year, we proved that the size of configurations measured this way, so excluding pointers to the initial term, is indeed a reasonable space cost model for the Space KAM. And by that, we mean that there is a linear overhead between Turing machines and random access machines on the one end and the Space KAM. I wrote KAM, but what I meant, of course, is that we are working with the Space KAM. So that's already very good. In this work, what we did was to reflect the space behavior of the Space KAM, which is reasonable. So from the point of view of complexity, it makes sense into types. So we still have these pictures if we work with the multi-types. The correspondence is still an injection. On the other hand, well, we immediately realized that what we want to measure, namely the size of closures, because ultimately environments and stacks are made of closures, well, it plays no role in multi-types. Multi-types do not keep track of the size of closures at all. A closure which will be substituted for any of the variable in gamma, well, it can be anything. It can be very deep. You cannot see anything about it by looking at ordinary multi-types. And then our idea was to then enrich multi-types by some information related to the closure, to the size of closures. Actually, this turns out to be quite simple and elegant. We just need to have a system of labels. So every multi-type becomes now a closure type, namely a multiset labeled with a natural number. And this natural number is simply meant to capture the size of all closures, which will, size of the closure actually, which will be substituted for the variable. And indeed, in typing judgments, variables are typed with closure types. So you also need this label. Actually, let's take a look at a couple of rules just to see what happens at the typing rules. Of course, the type system is not as simple as the usual multi-type system. You need a little bit more rules. Arguably, you need new rules because the underlying machine has changed. But for example, the rule of variables, well, it's the usual one. You don't need to do anything special, except for the fact that you need to take into account that whenever this variable occurs as in an intermediate configuration, well, its size morally it should take into account of the underlying closure, which is K, but only of the, but also of the stack, and that's why we have to take the size of A into account. The size of types just measure the size of the underlying stack. When you do, for example, when you type applications, well, you do it more or less as in ordinary intersection types, but the key here is the following. You have to take the max rather than the sum, because space is dealt with not by just summing up the weights, but by taking the max. And when you type a value as a star, so it's the final result, you should take into account that this final result can itself be a closure. So it can the size of the free variables, the size of closure substituted for the free variables should be taken into account. So the theorem, the main result is that the closure types are a sound and complete methodology for evaluating the space consumption of the space KAM, namely that every closed term receives a type with weight W if and only if its space consumption is precisely that weight. So wrapping up, so the contributions has been to show that a reasonable cost model for the lambda calculus can be reflected into types so that we give like a compositional flavor to it. The same thing can be said about the time cost of the space KAM, which, however, must be defined as more as a low-level time cost, because, of course, sometimes you have to copy environments, and this, from the point of view of time, can be problematic. And future and ongoing work is about, first of all, the generalization of all that to call-by-value machines. The space KAM has been generalized already to call-by-value. We are working on the generalization of closure types. And more interestingly, we are also working, looking at type systems in which this idea of measuring the size of closures becomes a way to do complexity analysis, complete complexity analysis. Now, of course, you can't say that because multi-types are not at all a way to do formal verification of programs, because type inference is by design an undecidable problem. Thank you very much.